Log on, tune in, find out. Another good idea from Cambridge.
This afternoon will be Alexander Rasin from Ariel University. We'll talk on infinitely many conservation laws for the discrete KdV equation.
Thank you very much. First of all, I want to say thank you to organizers of this conference that they invited me here, so thank you. And as it was said, I want to present a joint work with Jeremy Schiff, who is my supervisor, about infinite many conservation laws for the discrete quarter-Vec de Vries equation. So the outline of my talk is, first of all, I will explain what is conservation laws, and probably all of you know that, but I will explain what is it for discrete equation. Second, I will show methods how to generate new conservation laws, methods which allow to generate as many conservation laws as you want. And in the third part of my talk, I will show actually that these conservation laws which you generated, they are different. They are not trivial and they are not equivalent, so they're different. If you have any questions, please ask. Feel free. And first, I show an example of conservation law for continuous equation. The conservation law for continuous equation, for scalar continuous equation, is a partial differential equation, is an expression of this form. G and F are coordinates of conservation law, and let's say for this is quarter-Vec de Vries, continuous quarter-Vec de Vries equation, and this is examples of conservation law for quarter-Vec de Vries equation. I give just 3 conservation laws. This is well-known conservation laws, but actually it has infinite amount of conservation laws that it was proven. Yes. And next, what I want to say is what is trivial conservation law. So the trivial conservation law can be presented in this form: f is equal f0 minus dtf, and g is equal g0 minus dxf. So what f0 and g0 vanishes on as a consequence of the equation, and f small is any function, can be any function. So this is the general form of trivial conservation law. Any trivial conservation law can be written in this form. And actually, let's say, how can you define for continuous equation if conservation law is trivial? Let's say, if you have any conservation law, what first you do? You eliminate higher derivatives, right? Let's say if for quarter-Vec de Vries equation, if f will contain 4th order derivative in x or 5th order derivative in x, so you eliminate it until you eliminate all derivatives, which you can. And then this will give you f0 equal to 0, and so g0 is equal to 0. And so you'll get with this divergence, dtf and dxf. And to define this bit, to define that you have a divergence, you apply Euler operator, and Euler operator of derivative equal to 0. So in this way, you can always, for continuous equation, you can always define if conservation law is trivial or if it's not trivial. So it's not difficult at all. Now I want to show conservation laws for discrete equation. And
could you explain what can get from time to?
Sorry?
How to get conservation law from time to?
You mean conserved quantity?
Yes.
So integral of g with respect to x from minus infinity to infinity will be conserved quantity, will be constant. It won't depend upon t. So this is how can you get conserved quantity from conservation law.
What about f?
What do you mean?
You can only use partial derivative, not the time derivative to generate conservation.
Partially, don't understand.
I mean, what does it mean that you have f0 minus dtf?
This is trivial. So I present the form of trivial conservation law. I want to say what is the general form of trivial conservation law? Because you need to do, when you get conservation law, first question what do you ask? Is it trivial or not? If it's trivial, it's nothing, right? So I show that any trivial conservation law can be written in this form, where f0 is some consequence of the equation. Let's say you take equation. Or
Now I understood. Thank you.
Right? Now, now I want to.
Sorry, Alexander, you need to fix your mic.
Microphone.
Okay. Now, I want to show what is conservation law for discrete equation, and I consider quad graph equation because this is like basic equation where they're very simple. I mean, they can be very simple, and they're well known actually. So, yes. So this is a general form of quad graph equation. It depends upon k and l, and 4 points. I want to say that first coordinate is k and second coordinate is l. As you can see on the picture, k is a horizontal coordinate, axis, x, and l is vertical x. Just, I mean, just for you to know, because after that it will be important. And now the general form of conservation law is this expression. And as you can see, here you have SL, this is shift in L direction, yes, and I is identity mapping. So SL minus A is the difference. So it's very similar to continuous definition, right? The definition. Yes. And here F and G are also coordinates of conservation. Now, what is the form of trivial conservation law for discrete equation? It also has the same kind of form. So F is equal to F0 minus SL minus identity, F small, and G is equal to G0 plus SK minus identity F. And here also F0 and G0 vanishes like as the consequences of the equation. Now, yes. So the next question is it was a very big problem for me. How to define actually that this conservation law is trivial? So do you remember in continuous case what I told you, how to eliminate this F0 is G0? You eliminate high derivatives, yes? And then when you eliminate all high derivatives, it means that you went up to the end. But here, let's say this is the form of G, yes? So we know that let's say we have trivial conservation law, but we don't know about that. Now, let's say it has this form, and we know that it contains G0 and this difference. But we don't know how G0 look like. And in continuous case, we eliminated high derivatives, yes? But here, let's say we eliminate this point. How do we eliminate this point? We plug this 4-point equation. And instead of this point, we get this point, right? And I mean, the situation didn't get any better. And then, let's say, if you want to eliminate this point, we get this point, and so on. You can carry on as many as you want. And it doesn't guarantee that you will, at some point, eliminate F0, so it will be equal to 0. Or, let's say, what else you can do? You can apply Euler operator to this F or to G. Let's say, if you apply Euler operator to F, you will eliminate this bit, right? You will eliminate difference. But you will get Euler operator from F0. And it doesn't mean that it's not equal to 0 on solution of the equation Euler operator of 0. So you get, you don't get nothing good. So that was the problem. I didn't know how to solve it, and because you get conservation law and you don't know if it's trivial, if it's non-trivial. It was a big problem, but we found a way around it. How to define it, how to work with it. And first of all, I give a definition. So we say that conservation law for the quad graph equation is on the horizontal line if G depends only on values of U and M, where M is equal to 0. So G depends upon values on the line, on horizontal line. It doesn't matter what is F, but G lies always on the line. And we call this is horizontal conservation law. Now, and also vertical conservation law when F depends on values U and M, where N is 0. So this is a vertical line, yes? horizontal when G is on the line and vertical when F is on vertical line. And now we prove the following lemma, that for the discrete quarter-week de Vries equation, a trivial conservation law on horizontal line can be always presented in a form of sk minus I f, which means that this, if you go to previous slide, this G0 is equal to 0 always. If G is on horizontal line, so G0 is equal to 0. And we left just with sk minus I, we apply the Euler operator, it's equal to 0, so we can define that this conservation law is trivial. Yes, and also, let's say we have two conservation laws and we don't know if they're equivalent. So what do we do? But both conservation laws, G lies on the same line, on horizontal line. So then the linear combination of this conservation law, the Euler operator from linear combination of this conservation law has to be equal to 0. So this, if these conservation laws are equivalent, yeah. Okay? I think it's clear. Okay, and the same is true for vertical conservation law. So if F can be presented as a difference, if F lies on the line, so it always can be presented as a difference if conservation law is trivial. Okay, I hope it's clear. I mean,
Sorry, I have a few questions. First of all, is this restricted to the KdV equation?
yes, exactly. This lemma is restricted for KdV equation.
We can't do this for other quad graph.
I checked it for modified, which is H3 and ABS list if you're familiar with that. And also I checked it for cross-ratio equation. And it's true. And I think it's true for all equation. It just follows from some algebraic properties of this equation.
Okay, but you actually use the equation itself.
When I proved it, I used the equation itself. But yeah, up to now I proved it just for 3 equations. In article which we want to publish with my supervisor, we showed just for 1 equation, but for other 2 equations we don't show. Now.
And sorry, just again. And the general question, when it's not on the line, you have solved it.
But yes, if we have equation which is conservation law which is not on the line, so I don't know what to do. But actually there are such conservation law which are not on the line. For quad graph equation, not for all equation. For all equation it's clear.
But can't you not always bring it in a form?
No, there is
There is
this.
kind of freedom, well, an essential bit, but now it's on the line and then, yeah, just.
I can't bring it. There is I will show that it will be an example of conservation law, and you cannot bring it on the line. It depends upon K and L. I mean, if you're familiar with it, there is one which explicitly depend upon coordinates K and L. So over there it's impossible, I think. Probably some.
But I mean, if you have a configuration like you showed, you can always kind of actually indicate deform large bits of it on the line, and then you have maybe.
No, but then it will be something will be on K and something will be on L, and it will be together on 2 lines.
Yeah. You cannot do in general all of it, but you can kind of put the majority of that configuration on 1 line.
Yes, but then I can't guarantee that. Why do I need it to be on the line? Because then I can prove that on the line G0 is equal to 0. But if it's not on the line, if it's on the cross, so I cannot say that G0 is equal to 0 for this conservation. Okay, next I want to speak how to generate a new conservation law. And first of all, I want to show is Gardner method for Gardner method. And first I want to show Gardner method for continuous quarter-week de Vries equation. I think you're all familiar with this method, but I will repeat it. So for quarter-week de Vries equation, you have Backlund transformation. That is it. And first is Miura transformation. And together with this, it's called Backlund transformation. You can call it Gardner transformation. It's called differently in the literature. So you can see that second expression can be presented as in the form of conservation law. And now, V is a new variable in this backlog transformation. And what do you do? You expand V in the series of theta. In this series, you expand it in the series of theta, and then you define coefficient of theta. And then each coefficient will be a conserved quantity. And together with this is we expanded this bit. But when you expand this bit, you get another coordinate. And so you get each coefficient will give you conservation law. And as you can see, coefficient of this is trivial conservation law. Now, coefficient here is u. U is non-trivial. Next one is trivial. And after that goes non-trivial, trivial. So for quarter-week there is equation, it's every second is non-trivial. Yes. Now,
Excuse me.
yes.
This is also equivalent to when you use Lux pair.
What do you mean, Gelfand-Dickey? What do you mean, to generate conservation
If
laws?
you take the Lux pair for KdV,
Yes.
then this method is an equivalent to what if you use a Lux pair.
You mean the Gelfand-Dickey method, right?
No, how you want to call it. You can do systematic expansions in spectral parameters.
Yes, exactly. Yeah. Right. Now, we developed the Gardner method for discrete quarter-week de Vries equation. So this is actually the form of this discrete quarter-week de Vries equation. You know it. It's in ABS list is H1. Now, as you know that each equation from that list has auto-backlog transformation. This auto-backlog transformation comes from consistency on the cube. So if equation is consistent on the cube, you can always find this auto-backlog transformation. And now, you can see here U tilde is a new variable. U tilde is a new variable. And now, let's say we take this backlog transformation for some trivial theta. When theta is equal to beta, we get that U tilde is equal to U01 or U0 minus 1. And also so this is kind of trivial transformation, right? And also we get trivial transformation when zeta is equal minus alpha. So we decided to expand U tilde around this point, and theta around we expanded tilde around alpha plus epsilon, and U tilde is represented in this form. So this is analog of Gardner method. So what we need to do now is to find this VI. So if it's possible to find this VI, so each VI next to epsilon will give us a new conservation law. And we found V1, which is actually a very nice expression. And then we found the expression for VI. VI is equal to this form. And you can see that the right side depends just upon Vn, where n from 1 to I minus 1. So you can easily find next VI. You need to know previous VIs, and then you get a new one. Now, what else do we need for Gardner method? We need so-called initial conservation law. For quarter-week de Vries equation, initial conservation law was a part of backlog transformation. In our case, the initial conservation law has this form, so we found it. I don't know if it's connected with backlog transformation, I think so, but yeah, so it has this form. Now we plug instead of U tilde this expression, and we define these VIs according to these formulas, and we get the following F and G, and you can see that this is already we factored out this minus logarithm here and minus logarithm here, and this is already conservation law for discrete quarter-week de Vries equation. And now, other conservation law can be obtained by expanding this in epsilon. You expand this in epsilon, and each coefficient will give you conservation law. And we check that actually in continuous case you had every second non-trivial conservation law, and in our case you get all non-trivial. So, but actually it's not yet proved that it's non-trivial. I say it's non-trivial, but after that I will show how can you prove it. So this is Gardner method, and yes, and using this method we obtained we obtained many conservation law, but I give you first 4 conservation laws. So this was known, and now f1 is equal minus b a0, where b is equal to this expression, and a0 is equal to this expression, and so on. And what is interesting actually is that you can see a certain pattern, because in each conservation law, f depends upon b, and g doesn't depend upon b. And you can see that g lies on the line, and then all conservation laws, they miraculously stay on the line. And you can see there is no b here, here, and after that it's also no b. Okay. And after that result, we decided to apply Gardner method to other ABS equation, and we took modified discrete quadratic degrees equation, which is H3, and this is the auto-Backlund transformation, which is well known, and this is initial conservation law. And also we applied it, and we obtained several conservation laws, and it was seen that it works. And for cross-ratio equation, we also, this is initial conservation law for Backlund transformation, and also we applied it. We obtained also several conservation law, and it worked, basically. And I think actually, then the next question is this big equation, Q4. Yes, is the most important equation. And the problem is it's very difficult to work with it because of these Weierstrass functions and so on. And actually, I found this initial conservation law for this Q4 equation, but it's so ugly that I couldn't put it on the slide. I need 5 slides probably to put it on. And I'm trying to simplify it, but eventually I think I will publish it somewhere, I don't know. Okay. Okay. The next method which we use to generate conservation law is symmetry method. First of all, I give brief introduction what is Lie symmetry for discrete equation. So U00 we substitute with U hat, where U hat is written in this form, and here Q is a characteristic of the symmetry. So Q can depend upon K, L, and U, where U all shifts of U. I mean, it can be whatever. In case of local, it's a finite number of U's. In case of non-local, it's infinite numbers, whatever you want. And also we consider we change the parameter. A is a free parameter. I didn't say in the beginning, but I don't refer to alpha and beta. I put instead of that A. So yeah, we change also parameter. So the transformation of Ij also is very easy to calculate. It has this form, and then the infinitesimal generator will have this form, and then prolonged infinitesimal generator will consist of all kind of shifts of Q. And then how can you find the symmetry? You apply this prolonged infinitesimal generator to equation, and you say that this is equal to 0 on the solution, and then you get the equation. You get a functional equation. You solve it, and you get symmetries. Yeah, this is symmetry. Now, how can you use symmetry to generate new conservation laws? You know that this infinitesimal generator, it commutes with shift operators. That is basically the idea of this infinitesimal generator. It can commute with shift operators. So now, if let's say we have a conservation law, and we apply to it infinitesimal generator, because it commutes with symmetry, you can put x hat inside. After this bracket, you can swap it with bracket, and you get to sk minus a x hat f plus sl minus I x hat g, which is also the form of conservation law. So other conservation law will have the form f is equal x hat f, and g will be equal x hat g. And we say is also a conservation law. We don't say this is new conservation law because you can't guarantee it will be new. It can give you 0, it can give you the same conservation law, whatever, but it doesn't guarantee that it's always a new conservation law. Now, For Korteweg de Vries equation, symmetries and conservation laws, some symmetries and conservation laws are known. So this is not all symmetries and not all conservation laws. You have higher order, you have lower order symmetries as well, but this is what I need. I think you're familiar with these symmetries. So how can you generate how do we generate conservation law? We apply this symmetry X to the first conservation law, and symmetry Y to the second conservation law, and that is basically that is way how can you generate new conservation laws. If you apply, let's say, Y to first conservation law, you don't get a new. I mean, I checked. That is how I can say. Now, what I also want to know that X lies on the line, and here G also lies on the line. So when you apply X to G, you get something on the line. When you apply again, you get always something on the line. So as you remember, I said in the beginning that basically this is horizontal conservation law. And in the beginning I said that for horizontal conservation law, it's very easy to check if it's trivial or not, or if we have several horizontal conservation laws, if they're linearly dependent or not. So now we can do it. So now we have this conservation laws on the line, on horizontal line. So we prove the following theorem, that the discrete Korteweg de Vries equation has an infinite number of non-trivial conservation laws on the horizontal line, generated by repeated application of symmetry X to F and G. And during the proof of this theorem, we show that Euler operator of Gn is actually obtained by applying n time of operator X to G. So Euler operator of Gn is equal to sk minus 1 of Qn, where Qn is a characteristic of symmetry Xn, which can be obtained by commuting X and Xn minus 1. So first of all, I want to say what is this symmetry. You know that it was proven already by me and Peter that discrete Korteweg de Vries equation has an infinite amount of symmetries, and they can be obtained by commuting X and x0, x1, and so on. And all the symmetries are different and not equivalent to each other. So their characteristics also different and not equivalent to each other. So all these Qn's are different. And now these expressions also are different, and so the Euler operator applied to Gn will be they all will be different, and they are linearly independent. So from this it follows that all conservation laws which are obtained, they are not equivalent, because if they would be equivalent, so Euler operator applied to this conservation law will give you 0. To linear combination of this conservation laws will give you 0. And in this case, you can see that it's impossible that it will be 0, because this Qn, first of all, the order is different, and so it won't be 0. And here also I show the form of this Euler operator. Yeah. Okay. So this is the proof for that symmetry method gives infinite amount of conservation law. It doesn't prove that Gade method gives infinite amount of conservation law, but this is proof that symmetry method gives infinite amount of conservation law. So also, as I tried to prove the same kind of theorem for modified Korteweg de Vries equation, and it can be proven. I proved it, and I obtained that Euler operator of Gn has this form, which is different from previous. And also I tried to prove it for cross-ratio equation, and it also worked, and the Euler operator of Gn has this form. So it seems to me that I think it also can be proven for all equations from LBS list and also for Q4, but I think it's very difficult for Q4. Yeah. Okay, and now I want to present another proof that another proof that we get infinite amount of conservation laws, and this is already proof also for Gardner method and also for symmetry method. And we use continuum limit. And this is, first of all, this is non-standard continuum limit, because everybody thinks that Korteweg-de Vries equation can be continuously, you can obtain the continuous Korteweg-de Vries equation by continuum limit. But actually I don't know how to do it, and if anybody of you knows how to do it, please tell me how to obtain continuous Korteweg-de Vries continuous equation.
We know how to do it.
So you can show it to me, because it would be very interesting to apply it for if conservation loss for discrete equation gives also conservation loss for continuous equation.
That's in my thesis section.
It's in your thesis. Can I find it on internet? Or?
Yes. No, I'll tell you.
I see. So okay, because I was searching, but it's very difficult. Okay. Anyway, this is non-standard continuum limit. Actually, it's a very simple one. It's the simplest. What we do, we say uij is equal to this. Then we plug it into the equation. We expand it to Taylor series, and we eliminate everything apart from the coefficient next to the smallest h, smallest power of h. So we arrive to this equation, very simple equation. And this is A-canal equation, A-canal equation. And also we apply the same continuum limit to symmetries of Korteweg-de Vries equation, to discrete Korteweg-de Vries equation, and we obtain symmetries of A-canal equation. You can see they look very similar. Here, in our case, you have difference, here is derivative. So it is very similar. And now also we applied continuous limit to discrete conservation laws, and we obtain the following conservation laws. Also very similar to discrete equations. And just 1 second, yeah. And now what I want to prove. So if we prove that applying now this x to the first conservation law, we get infinite amount of conservation laws for this I-canal equation. So this means that we will have also infinite amount of conservation law for discrete equation, because this equation is sort of degenerate case. So if it's true for degenerate case, so it's true also for discrete equation. And that is what we did. We proved the theorem, which says that equation has infinite number of distinct non-trivial conservation laws. And they can be generated in this form. And we found the general form of Gn is 1 over ux to power 2n. So you can see that, first of all, these are non-trivial, and they're all different, they're not equivalent. And that is we proved for symmetry method. This we proved for symmetry method. And next, what we did, we applied continuum limit to Backlund transformation, and we applied Gardner, and we get Backlund transformation for I-canal equation, and then we applied this Gardner method, and we obtained also infinite amount of conservation laws for continuum equation. And this actually, for continuum equation, we can prove that this conservation laws obtained by Gardner method and conservation laws obtained by symmetry method, they're the same. But we cannot prove it for discrete case. I think it's so. I think it's true also for discrete case that both two methods give the same conservation, but we didn't prove it. Yes. Okay. Now, next, what we did, also we applied it for modified Korteweg-de Vries equation. And the continuous limit gave us the following equation. And you can see that this equation can be obtained from A-canal equation by this following simple transformation. And this transformation is so simple, so all results for this equation automatically you can obtain from previous equation. And then we applied continuum limit to cross-ratio equation. And that didn't work so well. First of all, we get this equation, which is not nonlinear equations. It's actually two equations. And then when we applied it to conservation laws, we get trivial conservation laws. So what we obtained, that this method is actually, this continuum limit this method is better in sense because it's easier. It's easier than the method which I showed before, this theorem. But it didn't work with all equation. As I showed you, it didn't work with cross-ratio equation. So because of that, I give two methods, because one of them works with, one of them is difficult, but it seems to me it works with everything, and this one is easy, but it doesn't work with everything. So, yeah. Okay. Oh, and yes, and that's it basically. And I want to say that all this what I present can be found in the article of Rasin and Schiff, and also I want to discuss the open problems which we want to research in the future. First, I say to you in the beginning that this Gardner method can, first of all, the Gardner method can be applied just to equations which have Backlund transformation. But and this Backlund transformation comes from three-dimensional consistency. And but let's say what can you do with equations which are not 3D-dimensional consistent? And so we need to know how to find the Backlund transformation for this equation, and also we need to know how to construct initial conservation law. Now the second what we want to research is connection between Gardner method and symmetry method, because we said that for continuous case it was trivial that they are equivalent. It was we proved that they are equivalent, but for discrete case we don't know. The next what we want to consider is realization of Gelfand-Deakin method, which is what you mentioned.
Yeah. I don't know if that's the right name.
And another what we want to do is to do something with this conservation law, to use it. So we think it can be used to show that the norms of solution is bounded, and this can be also very important topic. Yeah, it was quite fast. Thank you very much. Yes.
You say you had an example of a conservation law which was just not on the horizontal line and it couldn't be brought to the horizontal line.
No, it can be brought. It can be brought. This one. You see this f tilde is equal kf plus l f bar. So here this f bar is on horizontal line, but this is not. This is on vertical line, but f is not on the vertical line. So this is on the cross, and you cannot brought it, I think, on any line.
Could you explain what is on the vertical line? What does it mean? So do you have space and time?
You can say that first coordinate k in A is space and L is time. So k will be horizontal line and time will be vertical line.
So what's the conservation then?
What is what?
What is conservation?
What is conservation?
Yes.
What do you mean?
No, you have you build conserved quantities.
Yes.
I want to understand what is conserved. In what sense it is conserved?
Just 1 second.
So I thought that time is vertical.
Yeah, so you can say that
conserved quantities are just
conserved
localized
quantity
on horizontal line.
is the sum. It's infinite sum of g. It's infinite sum of g, and it's equal to constant. It's conserved quantity basically.
Yes.
And I don't understand what exactly do you mean when you say that you want to see infinite sum of g is equal to constant. This is so g is conserved quantity.
Yeah, I understand that, but I don't understand why you get a vertical line. It's like time direction.
It's time direction exactly.
Yes, so
No, but because
conserved quantity which doesn't depend on time. So why a vertical line?
no, yeah, I understand what you mean. No, it doesn't depend on let's say here points on vertical line. Like in continuous case, you can think about this like a derivative. So we say that, let's say, analog in continuous case, that g doesn't depend upon derivatives in time, but it still depends upon time. It still depends upon L, let's say. It still depends upon L, but doesn't depend upon derivative, let's say like this. And but it does depend upon, so there is no trick. Yes.
What do you mean by norms of solutions? There are singularities all over the place in your whole story.
What do you mean? Again, just 1 second. So, no, but actually, it's, I didn't research that. So, because that is the way how can you generally use conservation laws. You bound the norms of solutions, right? But I don't know how to do it in this case. So. And it is. I mean, it's. This question has to be. I'm not very mature, confident in this question. So I just.
This is not so much a question as a comment. I mean, another thing that you can use the conservation laws for is to get, if you do a reduction, say, to an ordinary difference equation, then you get the integrals of the ordinary difference equation from the conservation laws.
Yes. Exactly. You can,
Further questions?
Yes, I have a comment. Well, I actually, that's continuation of the remark which Frank made. Why don't you take the L operator and use the standard method of construction of conserved quantity?
first of all, we
Take
don't
the
have
place of the product of all operator, expand the spectral parameter, and get infinite set a complete.
First of all, you don't have L operator.
So construct it. So, because look, it's not funny. You have 3D consistency equation. That's Young-Baxter equation. So if you have Young-Baxter equation, you must have a whole algebraic structure which comes with the Young-Baxter equation, which includes elements. So the fact that you didn't know that, well, doesn't mean that it doesn't exist.
Hmm?
So there is a lux.
Yes.
Yes, there is a lux, but this matrix lux.
No,
right?
no, no. There is a scalar lux.
This is scalar lux.
For KdV. But there is a slight subtlety in terminology. The equation that you mentioned is a 4-point equation is actually the potential KdV. So an integrated version of KdV. The actual KdV is a derivative of that equation.
Mm-hmm.
And that equation has a scalar lux.
I see. I see.
And that, for that you can apply.
Okay, but this is a.
Yeah, but we can ask Seva, he's sitting here. Is there a lux matrix for this equation as well?
Matrix, sure.
For all
Of course
ideas.
we have. That's
No,
Is it 2 by 2?
no, but this is lux matrix. It's not lux.
So
no,
you
we don't need
multiply
lux
lux matrices along some path, and because of the property, it doesn't depend on the path. That's zero curvature condition. You expand it, you get conservation limit.
Yeah, but actually, this is Gelf and Dickey is actually this what we're speaking about. So we want to research it. I don't say that we don't want to do it.
No, that would be the, I think, simplest way.
But I should comment that this has been suggested by many people, but then when they sat down to do it, actually they never got it to work.
So, well, tell me what's wrong.
Well,
it's not explicit though if you
Yeah,
go
yeah.
at L.
You get in principle non-local conservation.
Isn't
But
that
then the version would be a combination.
yeah? But look, what do you mean local, non-local on the lattice in discrete case? It's all the same.
Well, if you want to apply the lux, this lux operator, the L operator, which you do have in this KdV case, then when you do the expansions, then you have to kind of do kind of discrete integration at some point. And so there's kind of something has to be a total derivative that cancels out, and that gives rise. That doesn't always it's always evident that happens. So that gives rise to non-locality. There are many cases known of non-local conservation laws. So I think your main contribution, I think, is that you show that you actually can get local conservation laws.
Yes, sure, because non-local it doesn't give anything.
Yeah, but what's non-local in the case of discrete vectors?
It's sum,
Explain.
infinite sum.
So perhaps if there are no more questions.
If anybody is interested, he can discuss with me any other questions. I will be very happy.
Absolutely. Okay, so let's thank our speaker once again. And the next talk will be.